Hello friends and students. So in the previous video segment we observed current divider rule, and here we will talk about voltage divider rule. Now why do we use voltage divider rule? So this rule is actually used so that we can calculate the voltage across one of the elements here. Now here I have considered an example where two resistors are connected in series, or two inductors or two capacitors are connected in series. So when elements are connected in series, the current flowing through them would be the same. So if I consider two resistors connected in series, the current flowing through R1 and R2 would be the same, but the voltage drop would be different. So let the voltage across R1 be V1 and let the voltage across R2 be V2. So we need to find V1 and V2. So similarly here in these two cases, I need to find V1 and V2. Now when resistors are connected in series, what is the equivalent resistance? So R equivalent is R1 plus R2. So I know that V, the total voltage V, is I into R equivalent, or it is I into R1 plus R2. Now what is V1? V1 equals I into R1. And similarly, what is V2? V2 is also equal to I into R2. Because the current flowing through R1 and R2 would be the same, which is equal to I. Alright, so now what do we need to find? I need to find V1 and I need to find V2. Now from this expression, what is I? So I equals V, the total voltage V divided by R1 plus R2. So let me substitute for I in these two. So what is V1? V1 is I, which is nothing but V divided by R1 plus R2 into R1. And what is V2? V2 is I, which is V divided by R1 plus R2 into R2. Alright, so what does voltage divider rule state? So the voltage across the first resistive element is the total voltage into the same resistance divided by sum of resistors, and the voltage across R2 is the total voltage into the same resistance divided by the sum of resistors. Now let us assume that if there are n number of resistors connected, so this is R1, R2 and Rn. Now suppose I want to find V4, the voltage across the fourth resistor. So it's going to be the total voltage into R4 divided by the sum of all the resistors R1 to Rn. So that's going to be V4. So it's as simple as that. So now let's find out what would be V1 and V2 in case of the two inductors. So similarly here also I have current I. So the same current I flows through. So the same current I flows through L1 and L2, and let the voltage across L1 be V1 and the voltage across L2 be V2. So I need to find V1 and V2. And what is L equivalent? So we know that L equivalent is L1 plus L2. So when two inductors are connected in series, the equivalent resistance is just the sum of them. Alright, so we know that V equals L di by dt. So it's going to be L equivalent di by dt, or L equivalent is L1 plus L2 di by dt. Alright, so what is di by dt? It is nothing but V, so the total voltage V divided by L1 plus L2. Now what is V1? V1 is L1 into di by dt. Why is it di by dt? Because the same current I flows through all the inductors connected in series. But what is di by dt? It is V by L1 plus L2, isn't it? So therefore this is L1 into V divided by L1 plus L2. And I have V2, which is L2 into di by dt. So again substitute for di by dt. So I have L2 into di by dt is V divided by L1 plus L2. So again we find that the expressions of V1 and V2 are very similar to that of the two resistors connected in series. So what is the voltage across the first inductor? It is L1 into V, the total voltage V into L1 divided by the sum of inductances. And then what is V2? The voltage across the second inductor is nothing but V into L2 divided by L1 plus L2. So now let's find out the voltage across the capacitors C1 and C2. So again I have current I which flows through C1 and C2, and let the voltage across C1 be V1 and let the voltage across C2 be V2. And we know what is the equivalent capacitance. So when capacitors are connected in series, C equivalent is C1 into C2 divided by C1 plus C2. Alright? Okay. So now what is the capacitance? C equals Q by V. So or the equivalent capacitance is Q by V, where V happens to be the total voltage, and remember Q is the charge which remains the same across both the capacitances C1 and C2. So therefore C equals Q by V. And what is C1? It is Q by V1. And what is C2? It is Q by V2. Alright, so I need V1. V1 is Q by C1 and V2 is nothing but Q by C2. So here we need to substitute for Q. What is Q? From this expression, Q equals the total voltage V into the equivalent capacitance, which is C1 into C2 divided by C1 plus C2. So I will substitute for Q here in these two expressions. So V1 equals Q is V into C1 into C2 divided by C1 plus C2, this is Q, into 1 by C1. So C1 gets cancelled. So V1 is V into C2 divided by C1 plus C2. So here, in case of the two capacitors connected in series, what is the voltage across the first capacitor? It is total voltage into the other capacitor C2 divided by sum of capacitances. If I consider this expression, V2 equals Q. What is Q? It is V into C1, C2 divided by C1 plus C2 into 1 by C2. So C2 gets cancelled. So V2 is V into C1 divided by C1 plus C2. So what is V2 here? V2 is nothing but the total voltage V into the other capacitance C1 divided by sum of capacitors. So here in this video segment we have seen voltage divider rule, or we have used voltage divider rule to find the voltage across one of the elements where I have two elements connected in series. It may be two resistors connected in series, or two inductors connected in series, or two capacitors connected in series. So is it possible for us to find the voltage across one of them? Yes, it is. Again, we observe that the expressions for the resistances and inductors connected in series, that is, the voltages are very similar and they are different for capacitors. So I hope you have found the video informative. Do not forget to like, share and subscribe, and press the bell icon to get notifications of further uploads. And to watch all the other videos in network theory or electric circuits, click on the I button, or make sure that you go through the playlist network theory and you'll get all the videos in this subject. And thanks for watching.